Okay, so we can start, and let's welcome the first presenter, Fan from Intel, to give us the speech about the crypto. So, Fan, it's your turn.
Okay, thank you very much, Chen. Let me share the screen. Okay. Okay. Hi guys. Thank you very much for joining this talk. And it's a unusual event. I really appreciate the chance being given to make this speech. So my name is Fan Zhang. I'm a network software engineer in Intel Shannon, Ireland. And I've been the VPP Crypto and IPsec tech lead role in Intel for a few years now. And I've been an active DBDK crypto maintaining role and upstreaming role. So my today's talk is Warp Speed of Crypto, a new DBDK crypto dev raw data path API, and is used in FIDO VPP. So this is the agenda of today's talk. So first, more of not just a problem statement, more of a motivation. Why we want to propose this new API. So I will spend quite a bit of time to discuss the new API. So so the new data structure, we will get involved with the new API, and the raw data path session context data, and the unique way of enqueue DQ. And last year I will describe how this is used in the crypto. This API is adopted in the FIDO VPP, and in the end, the summary. So first, why we wanted to propose this new API. So DBDK Crypto Dev is great. It has been widely used to accelerate the network traffic package encryption. But there are some limitations. So first, it's based on the assumption that all the data is described by the DBDK RT-MBUF data structure. Which is 128 bytes long data structure, leave alone the head ROM and tail ROMs. And you have to allocate extra data structure called RT crypto op to describe your crypto workload in addition. And you have to put your MBUF source and destination pointer into this data structure. And you have to use pre-allocated non-expandable mempools for these MBUF and the crypto op buffers, which I know that anything guys has already did excellent presentation on the expandable mempools, but for now DBDK Crypto Dev still stuck on this. And it has the best effort based enqueue and DQ operations, which means you have to enqueue you want to enqueue like 32 buffers. And when the crypto dev device queue is full, you probably can only enqueue half of them. And but you won't know that until you get the enqueue results. The same thing happens in DQ. All these limitations are there for the sole purpose, extreme performance, of course. So using RT-MBUF, you get the packet straight away from I/O to the crypto device, and you have a compact data structure to describe what you exactly crypto workload needs to be processed. And you use mempool to make sure all the packets are aligned and all the buffers could be accessed directly, no matter its software, hardware devices. But it is based on assumption that your implementation is written purely on top of DBDK. So what if that means you need to use DBDK as I/O, and you need to use CryptoDev API, on top of MBUFs you got from your I/O. So what if you want to use your CryptoDev API in your crypto driver engine? Let's say you have an application, you want to write the DPDK CryptoDev API to enrich your application's crypto processing capability. But let's say you already have your own crypto data structure. Let's see. I have two examples for that. So first, DPDK WoodIO Crypto. So for some of you may already know, but some of you may not. So DPDK WoodIO and WeHost Crypto is DPDK's solution to the virtualized crypto processing. So the WoodIO crypto driver in the VM will send the crypto request through the standard the WoodIO crypto spec to the host. The host uses WeHost Crypto to process this data. So WoodIO Crypto has its own data structure, and data is described by the WoodIO ring descriptor. To process the WoodIO Crypto workload with the DPDK CryptoDev, one must carefully dequeue from the WoodIO ring. And why is that? Because the WoodIO ring basically, when you already dequeued some buffers from the WoodIO ring, there's no way to put it back. So if your crypto devices doesn't have enough room to process these buffers, you have to cache them, or you have to drop them. And then you have to get the RT crypto op buffers from the crypto op mempool. And also you have to get RT mbuff buffers from the mbuff mempool, because WoodIO spec doesn't contain any mbuff data structure information. You have to allocate it. So then you need to translate the WoodIO ring descriptor, if it's crypto, and into the RT mbuff, which contains all the data information. Then you have to translate the WoodIO crypto spec data into the DPDK RT crypto op. Once all this is done, you want to enqueue them into a DPDK CryptoDev device queue, and then you do a dequeue. So once you have dequeued some crypto ops, so let's I have said you have to carefully dequeue from the WoodIO ring so your enqueue won't fail. After this is dequeued, you want to translate the DPDK crypto operation status back to the WoodIO crypto operation status. That means you have to scan all the crypto ops you dequeued one by one, and you pass the status from one to the other. Once this is all done, you still have to put DPDK RT mbuff and the RT crypto ops back to the mempools. Okay, I want to make 100% make sure everything works. Give me 1 second, sorry. Does my screen sharing okay?
Yeah, it's okay, Fan.
Okay, and then I'll continue. Sorry about the interruption. Okay, next, let's see a second example. The WoodIO Crypto is the one that we expose some problem. If we use DPDK CryptoDev in the VPP Crypto, we have not a problem. So this example is the DPDK CryptoDev engine in the VPP Crypto asynchronous infrastructure. So for some of you don't know, FIDO VPP is a network processing application that handles user stack, network stack, including crypto processing that uses in its IPsec framework. So same as WoodIO Crypto, VPP Crypto asynchronous infrastructure also has its own data structure. That is used to describe both the data and the crypto operations together. In addition, it wraps up to 64 crypto operations in a single crypto frame, which means so it's a pointer to a big data structure containing up to 64 buffers. It requires enqueuing only one buffer pointer at a time and expect to dequeue one buffer in return. That also means the complete enqueue and dequeue of the whole frame of up to 64 buffers. It may contain less or nothing. To overcome this problem, we had to first, again, we need to carefully check if we have enough room to store all this buffer. So we have to keep a runtime counter to see if there's room left to enqueue the whole frame, which is up to 64 buffers. And on dequeue, you probably want to dequeue exactly amount of packets in a whole frame at a time. Most likely you will dequeue half of the frame. So you have to cache half dequeued frame and use a very complex logic to track the dequeue status for every cached frame. So furthermore, we have another problem. I call this double looping and double translation. What does it mean? When your application is written purely on top of DPDK, you get an RTM buff straight from the DPDK IO driver. Then you can use them directly on top of the crypto op. But for VPP, the situation is slightly different. So you need to loop all the packets and assemble them into the the VPP crypto frame. And in your CryptoDev engine, you have to again loop all the packets in a frame to assemble them into the crypto op. So you need to loop them twice, and you need to translate them both twice. That actually hurts the performance even more. So in summary, to enable DPDK CryptoDev on top of an application with existing crypto infrastructure, you may have some performance bottleneck introduced. You have to have extra mempool get and put operations for RT crypto op and RT mbuff. You have to have extra translation cost on converting implementation data to the DPDK crypto one. And you have to have extra loop for another translation when in the crypto driver. You have limited control over enqueue and dequeue burst operation that force the enqueue check and dequeue cache. So to make DPDK CryptoDev more friendly, so that's what we thought when we implemented these two projects. DPDK CryptoDev should target raw buffer, so it has wider application usage. It could be used not only for encrypting network traffic coming from DPDK IO driver, and it could be more friendly to external libraries and applications. That's the reason we propose this DPDK CryptoDev symmetric raw data path API. So yeah, all the data structure that in the new API, I need to have to describe them first. So first, we need to think about the data. Rethink about the data to be put into DPDK CryptoDev. So it should support any data, not mbuff centric. The only data that CryptoDev actually interested in the 128 bytes mbuff header is only data virtual and physical address, only the data length, and the scatter list represented by the mbuff chain. So that's the reason we present this RT Crypto SGL new data structure to describe the data to be processed. Nature contains an array of RT Crypto WAC that contains only physical and virtual address and the length of the buffer. And you got a number of WACs for the present of the SGL. Nature using these to replace RT mbuff has the advantage of reduced memory reads, more compact crypto operation data structure, and you are free from the dependence of RT mbuff. So to describe both the data to be processed and the additional data pointer, we propose this RT-crypto-sim-WAC. So it's already in the CryptoDev that it mainly used to process synchronous crypto. We further enhanced it to be able to process by the hardware as well. So it's as you can see over here, you have number of packets in this data structure, and you have the SGO data structure I just described, and you have a bunch of pointers to represent IV digest or AAD. So this is for the burst in queue of packets with the same session. So different session, you will have a different data structure. And the container only requires data fields for all symmetrical crypto operations. So one great advantage of this is you don't have to allocate this buffer from the heap. You can directly allocate them from the stack. And it's way faster to allocate them and release them, because CryptoDev itself only interested in the user data you put into, so it can be dequeued later. And it has simpler status in return for in-queue. It pushed into the status array, either success, 0, or error number. So with all these here, we did another refactoring on the device queue session abstraction. So when you in-queue a burst of packets into CryptoDev queue, you need to provide CryptoDev device ID, queue ID, and the session data. So when we were thinking that, we think, why don't we, abstract them into the same data structure? So each has, the reason for that is every thread normally owns a CryptoDev queue pair and tends not to change it frequently. So basically, it probably never changes during the application lifetime. And a queue pair pointer could be directly mapped into this data structure. And in most cases, multiple consecutive packets will share the same session, which is the same flow. So you can map the specific in-queue and dequeue handlers into this data structure. So to avoid a great branch in a single in-queue and dequeue operation, which if you see the CryptoDev in-queue and dequeue implementation in the CryptoDriver today, you will see easily thousands of lines of information over there. Because of the great branches, you have to process cipher only, hash only, chain, AEAD, all this kind of processing in a single function. Using this could help make the code clear and easier to maintain and more performant. And in case of session change, you only update these 6 function pointers. Naturally, the cost of this is minimum. So when you have the session device configured and you have the session context briefed and just now configured, you can start with the data in-queue. So there are 2 types of in-queue functions. First, in-queue burst. If you can see from the raw in-queue burst API over here, it basically it's equivalent to the existing RT-CryptoDev in-queue burst operation. So you have the next option is called an in-queue single. The in-queue single function will help to remove, so it only in-queue a single data at a time. And the driver should cache the data into the crypto device queue. Only when this RT-CryptoDev raw in-queue down function is called, the device will start processing them. This helps to avoid this double looping problem I was just described. That saves one layer of translation altogether, because assembling these data structures from your application's driver's code, crypto code into this is the cost is minimum because it's the raw data pointers. And secondly, when you push one request into the crypto device queue at a time, you basically have zero cost on have to loop inside the crypto driver again to assemble the two driver specific crypto requests. So after expected, so once this RT crypto enqueue done is caught, the device will start processing them. But let's say you want to enqueue 64 and you end up enqueue 63. So that is a problem to you. How you can avoid that? You abandon all this. Let's say you enqueued only one, and you want to abandon this in one enqueued data and try next time. Naturally, you can do that to call the session context, the raw DP context buffer one more time to reset the context data. I will describe the detail a bit later. So the same thing happens in DQ. We designed the DQ function. The user can use callback function over here called RT get DQ count T to pass the first user data to get the data to get the how many packets you wanted to DQ. Naturally would helping to have a fine-grained DQ count, and your user can use another callback to set the DQ the status in flight to save status translation. For example, for QAT, the QAT has its own data status. The driver in the older API needs to translate them into the RT crypto dev status, and you need to loop the DQ'd ops to translate into your own data status flag. With this API, you can save one status translation. And instead of looping all DQ'd user data, there is a narrow, to find if that is narrow, number of success returned value could be used to compare number of packets you DQ'd. If they are equal, nothing happens, everything's great, you can continue. Only when they don't match, you need to check the DQ status of each flag to see what package is from. Again, to abandon DQ, simply reset the context number. So DPDK-QAT PMD has already supported raw data path API. So we have each symmetric crypto algorithm has its own handler, so which helps us to reduce the code size of each different application implementation way, and it saves a lot of branches, and it's updated only when the session is changed. So if you have session handler for one session, and once you change the session, you call this session CTX again to replace by chain, for example. Then in QAT, the shadow copy of the Q pair, the head and tail are stored in the DPCTX. And during the initialization, so the shadow Q data is used to cache what you already enqueue and dequeued. So when you enqueue a package, the shadow Q tail is updated. When you dequeue a Q package, the shadow Q head is updated. Only when you call enqueue down or dequeue down, the device will start working, and basically we'll merge the shadow Q head and tail back to the main buffer. So CryptoDev raw data path API and the QAT support was merged in DPDK 2011. In VPP 2008, we have unofficial support to this raw API, and we already showed the performance to the public. And VPP 21041 has official support to this API. So it has a few advantages: smaller memory footprint. You save the one crypto op pool per socket. It's more efficient. You save the one loop translation cost from VPP crypto frame to the DPDK crypto op. You save the crypto op status translation into crypto op operation status. You have less cost in cache to have the Q frame. So instead of have a ring of the Q size length, you can use a minimum buffer to just cache if you want to cache half the frame, half the queued frames. So, and the IPsec performance improved by 15% period from no matter how big the packet size is. Okay, to summarize, in general, DPDK CryptoDev DataPass API has a few advantages. Compact, flexible crypto data structure. You're no longer dependent on MBUF. You can allocate a buffer from stack, and you only include the data you're interested in as the user data. You have all-in-one operation context. It is flexible and fine-grained enqueue and dequeue operation. It avails close to native symmetric crypto performance to the library on applications. Those are not MBUF-centric or with its own crypto data structure. So API has been successfully integrated in FIDO-VPP, proven easy to adopt, more flexible, and more efficient. So we hope, CryptoDev Symmetrical Raw DataPass API is one of the first sets API DPDK contains to welcome the outside world integration of DPDK CryptoDev library. So we hope this work would encourage more changes and more patches submitted to DPDK that make DPDK a friendlier place to the outside application adoption, and it would be much wider to adopt to an even higher level of DPDK framework in general. That's the end of my talk. Thank you very much. So I will take some questions now. Okay, Thomas has, how much PMD code can you share between RAW and MBUF data path? In CryptoDev, you can say 90%. Because of CryptoDev only interested in the MBUF buffer address and IOVA address and the length. And if there is if there's the next flag or next segment flag presented, you will access the next the next segment, the MBUF next pointer, and that's it. So that's the reason I say it most likely 90% of the buffer. But for generic IO driver, it will be more problematic for sure. Sorry, I was too excited. I forgot to turn on my camera. So I used last 3 minutes to share my face. Thanks, Thomas. Could this framework be independent library? For now, I'd say not easy, because we only make their data path enqueue and dequeue independent. So we remain their CryptoDev session and their device configuration is still remaining intact. So this is because of the device configuration and the queue pair setup, or the session creation is really complex, and it's really tied it up with the DPDK framework already. And to make this independent, completely independent, you're basically you're still writing a brand new framework to support these old CryptoDev devices. Yeah, for Wikas, this is a good idea for lookers at crypto. But for inline encryption, decryption, and packet data path, RTM buffer integration is a must, right? And this is for sure, yes. And for inline, as I expected, when you configure inline crypto to a NIC, which you would expect that the packets, the plain packets, when you send out through the NIC, the packets should be already, encrypted by NIC. When you receive the packets from NIC to the memory, it should already be decrypted. So it's not in the crypto scope. The crypto itself would be treated as a control panel. So for MBUF, that is different scenario in this case then. I hope that answers your question, Wikas. Sorry, Ashish. The raw API applicable only for bulk crypto symmetric? At the moment, it is only for bulk crypto, and it's only for symmetric. So we use this way to present our idea. And originally, the code was designed to support asymmetric crypto as well. But for now, because there's no TMD to support this feature, so we decided to leave that alone aside at the moment after discussing with the maintainer and other developers in Intel. So once the asymmetric is to be supported, the API could be expanded easily. I hope that answers your question as well, Ashish. Okay. I guess that's it. Thank you very much, guys, and have a nice day. Enjoy the show.